Yeah, welcome back, everyone. Thank you for being on time. And welcome to our afternoon sessions. We have 4 interesting talks. The first one is about the challenge of finding and retrieving unstructured information, an interesting challenge. I've also struggled with myself, so really looking forward to this talk. Kristian from Vespa, I think probably needs no introduction, search veteran. Is talking about how vision language models help with that task, and he is introducing ColPali to us. I'm right. Stage is yours, Joe.
Thank you very much. Yeah, first of all, it's great to be here at Haystack again. It's a really great conference, really high signal to noise ratio. I'll talk about a topic that I'm very excited about, and the pitch is what you see is what you search, and using visual language models for PDF retrieval. I do believe that this is the kind of future of retrieval. But in this deck, I'll talk about introduction, indexing and searching PDFs, talk about vision language models, VLMs, ColPali. I don't know how many of you have heard about ColPali before Trey's talk this morning. Couple of hands. Good. So you will learn about ColPali today. And scaling ColPali, RAG, of course, retrieval augmented generation using VLMs, and then QA and resources. And also, if you want to jump to the deck, you can scan that. So how many of you have tried to index PDFs? Quite a few, okay? So this is, I think it's quite amusing. I think Charlie, I asked him if he could do the intro on how difficult it is, but he said I would use all your time. So we're not doing that. But PDFs can be quite complex. They can contain like visual, infographics, tables, charts, images. And at the start of the ChatGPT, RAG wave, vector database, chat with your PDFs, whatnot. Actually, chatting with the PDFs was one of the kind of primary Hello World use cases. Because there's real value in that, because a lot of information in the world is buried in these PDFs. And to do that, you need some kind of extraction, because you want to map it to text. At least that's what we used to do. And then you have to chunking, text embedding, and whatnot. But extracting text out of these documents is quite messy. It's maybe not so visible here, but this entire element of this PDF is not extractable because it's an embedded image. So you can clearly see there's text, there's numbers here. And if you do this by text extraction and your manager is trying the new search interface and is searching for something that is present in this information, it's not going to be retrievable. You won't be able to find this document, right? And this can be very hard to explain to people that are not used to technology, right? But I can see the text there. Why can't your search engine retrieve it, right? It sucks when you say, yeah, but it's an embeddable image. What do you mean by embeddable image? The text is there. I can clearly see it, right? And you go, yeah, but not only that. So then you turn to some text extraction routine. And on the right side here, I actually display the text if you're using a popular way to extract text. You can see the headline, sustainability and nature, has become nature sustainability, one word, right? Which then makes basically both those two words unretrievable, because in a regular lexical text search system, right, it will be indexed as one token. So if someone searched for nature, it will not be retrievable, right? So it's messy. And in addition, ordering as well. You can see that the first chunk of text is we manage biodiversity risks and mitigate impacts, which actually is all the way down here, right? That's the first chunk in the text extract. So it's messy. But why do we extract the text in the first place? Why do we try to move this kind of complex format and convert it into the text domain? Well, of course, we need to convert it to something that makes it searchable. And we need to have it in text because we're going to use something to search it with. And historically, we would use Apache Solr or Elasticsearch or OpenSearch or Lucene or Vespa or something. Or we would use like a fancy embedding model, chunking, whatnot. But we would have to extract it to text. And there are a lot of companies around, or technologies as well. Apache Tika is a well-known technology for extracting text out of a wide range of document formats. It's great. Llama Cloud also, that's the Llama Index people, they also went into this route. They thought, okay, we're going to build our business model around extracting data out of complex documents. And unstructured also, get your data RAG ready, yati yati. Tesseract is one of the most popular OCR frameworks, a lot of complexity. And then we'll talk about vision language models. So how many of you have tried ChatGPT or GPT-4 with vision capabilities? Have you like tried uploading an image, asking questions about it? Okay, so quite a few. That's good. So what is a vision language model? Broadly, these are multimodal models that can learn from both image and text at the same time. So on the top here, here's the VLM. There's a text input, there's an image, and the model generates some text. And these are typically generative models. All the demos are around cats. You can ask the question, upload some image of a cat. What is the breed of these cats? And you get a response. And this is my view of VLMs, been for quite some time, that you use it for searching cats, to find cute cats on the internet. And I made this overview. And we are unfortunately very soon in 2025. This year flew by. This is an inaccurate summary of the VLM landscape. We didn't have very powerful VLMs at the start of this year. So at the start of this year, VLMs searching cats, not so interesting. Then we got some powerful models from OpenAI. Then there's been a bunch of models, and I made this diagram on Wednesday last week. And just after that, there were two new powerful vision language models released. Molmo from AI2 and Llama 3.2 from Meta. And it turns out that these can do more than just searching from text, or searching for cats, I mean. So Polygamma is one of these vision language models that came out earlier this year. It was released with open weight, so you can use it under certain terms. It's not an open source per definition model. But it came with, and it was trained on multiple different tasks. And one interesting aspect of it was that it had pretty strong, what we call OCR capabilities, or the ability to read text from an image. This enables it to do question answering. So on the right side here, I have uploaded the PDF page, or a screenshot of the PDF page. And this part is not extractable because it's an embedded image. And I'm asking, what is the percentage of produced water that is reused? And it answers 40.56%, which is, in this green bottom here, says 45.6% of produced water is reused or recycled. That's quite powerful, right? That you can actually answer a question like this given one image of a PDF, right? So that's actually real progress of what you can do with these type of models. And here's an example with a different open source, open weight, open source model from Quinn. This was released, I think, 4 weeks ago. And for fun, I uploaded an image from our Vespa performance dashboard and asked it, what's in the image? And I could basically use this to explain to managers at Vespa what are we actually looking at, because it so accurately describes what's in this photo. It says that there's performance test here, the different versions of the software labeled as X, Y, Z, which is the versions on the X-axis. It understands that the latency on the Y-axis is latency. It also says that the blue lines, bits, Hamming, shows a significant decrease in latency from version blah, blah, blah to and indicating improved performance. So it's quite astonishing that it can actually take a screenshot, explain to me what's going on here, right? I know there are a lot of like executive dashboards, graphs, charts, whatever. You can just enter the VLM and it will summarize it for you. So, and these insights into the actual power of these VLMs made the researchers behind ColPali to see, can we actually use these VLMs for retrieval? And what do we mean by retrieval, right? So in the previous example, we basically gave the model, here's the screenshot, here's the question, okay? So you could do that if you have a collection of, let's say, 100,000 images, you could kind of ask one model for one image of a time and then ask to, score them, right? But it will be quite time consuming because these models are quite big, they have high latency. So ColPali, the idea behind ColPali is to use the capabilities of these VLMs and extend that capability for document retrieval. So let's say we have 100,000 PDFs, we want to search across them efficiently. And they also argue that in the practical industrial settings, we don't have the luxury as well of pre-processed data sets, right? So when you talk about, you see numbers here, NGCD from MS Marco and so forth, but there we are looking at clean, pre-processed text data sets, right? We have the passages, they're clean, nicely formatted and everything. We have the queries, they are nicely formatted, and we measure NGCD, we measure chunking, we all kinds of stuff. We look at the MTEB leaderboard benchmark, right? But in the industry, when you want to take PDFs and make them searchable, it's quite messy. It's quicker that actually is the bottleneck of your performance end-to-end than whatever embedding model you're using, right? As you saw that the text extracted was not really well done. And that's what they're trying to achieve with ColPali. I'm not associated with any of these, but when I saw this paper in July this year, I was like, oh my God, this is huge. And I've ever since then actually invested a lot of time in it. On the top here, this is a diagram from the original paper where they kind of outline their method. And I'm not going to spend too much time on this, but they argue that a regular retrieval pipeline for PDFs would include text extraction, OCR, layout detection, then chunking, embedding, and whatnot, while they're replacing all of that complexity with a single model that takes the screenshot of the page as an input. And ColPali is actually short for ColPaliGemma. So PolyGemma is the visual language model backbone. And Col is from a concept called contextualized embeddings over. So, and we will get into that, what that means. But ColPali generates these multi-vector embeddings directly from the screenshot of the PDF page or a text query, and is using this visual language model as the backbone. And then at the scoring time, similar as you're doing a BM25 score or a multi-vector score or a single vector score, there's some interaction between these text query vectors and the embeddings that you get from the screenshot. And thankfully, Trey gave a great talk this earlier. I talked about bi-encoders, cross-encoders, and a lot of different names. So here it is, it's a bi-encoder architecture because the architecture that you're suggesting enables this offline indexing. So you can take all the pages you have, and then you can process them, produce embeddings by them. And when a user shows up at query time, we can do the matching, okay? Instead of having to input both the page and the query at the same time into the model, which is more of the cross-encoder model that Trey talked about. And what's the benefit? Well, you can have matching without text extraction, so you can score documents in a collection without having to go through the text extraction step. You can avoid OCR. You can avoid layout detection to identify figures or tables. You just embed the screenshot. Simple approach engineering-wise, you don't have to have a very complex document processing pipeline. Also, as we will see, it also has better relevancy when we compare it with more traditional methods. And I believe it's a future direction for document retrieval. Essentially because can you print the document? It means that you can actually index it with the ColPali approach. So it's more universal for different types of file formats than ever before, because it's the same kind of technology when we are sending something to the printer, right? We're essentially sending an image, right? And now it gets harder, so you have to focus. So using this page, and the page is actually divided into a grid of 32 times 32, what they call patches. And essentially, one image is worth 1,000 words. We say something like that in Norwegian, at least. I don't know if it translates to English, but in reality, with this VLM, one image is worth 1,024 words. And each of these patches, though I didn't draw all of them because my drawing skills are not so good, but each of them are represented as a vector representation. So a 128-dimensional vector. And we can call this like the latent vector space, where we project all the images into so that you have a lot of the vectors for each of these cells. At the same time, it's also matching text. And you can, because you get the model access both text and the image at the same time. And the ColPali architecture, they prefix the input with like describe this image. Because they didn't want to do any kind of text extraction. In theory, you could actually extract text. Like if you're doing e-commerce search, you have the product title, you have the product description. You could actually input both representation at the same time. So when you're querying in text, you could actually attend to both the product description and the image. So there's a lot more potential in this. And it deals with page level representation, right? So it doesn't embed the whole PDF document. So maybe you have a PDF document of thousands of pages. It obtains one representation per page. And in the Vespa language, you can represent this as a tensor. And it basically is a tensor which has one map dimension here called patch. And V128 stands for a vector of 128 dimensions. You can see this as if you're familiar with the map data structure. There's a map where the key is the patch and the vector is the value. So this is the representations that you obtain on the document side. Same on the query side, you're mapping queries into embedding vectors, and you have an embedding vector per query token or word. These language models, they basically tokenized text. So what is the percentage of produced water that is reused will be tokenized into predefined tokens in the language model. And each of those are represented as an embedding. And each of the tokens has a vector representation here. So you have basically a token level embedding representation. And then you have a similarity phase between these two. So when you want to score a document or a page for a query, you have this kind of interaction between this. And this interaction is called the sum of maximum similarities. It's also called late interaction. I will explain this in more detail in the next slide. And this is where the name is from. So ColPali is essentially contextualized late interaction over embeddings from Polygamma. You can replace Polygamma with a different VLM, right? So you can have col llama 2 or col quan 2, as we will see. But so you can't actually replace that, but we'll get to that. So what is the maxim? You essentially compute a similarity matrix between all the query tokens and all the patch tokens on the image. So I try to illustrate this here, where I've divided the page into just 4 cells. Okay. So, and each of these cells are represented here in my example as a 2-dimensional vector. In reality, in ColPali is 128 dimensions, right? So I have 4 cells. So, and you have 2 query tokens, so water and recycle, and each of them are represented as a vector. Then you take the representation for water, and you calculate the dot product against this cell, this cell, this cell, this cell, and you find the maximum. In this case, it's this cell. So the example is made up, okay? So for illustrative purposes. Same with recycle. 36, this one is the best matching. And the final score for this page, for this query, is 74. Is that clear? Is it? But in reality, right, you have a lot more of these patches. There are higher dimensions, 128. But that's the idea of this maxim. Similar for text, for ColBERT, which is the text version of this. You basically just have text and text on both ends here. But for Polygamma, for ColPali, you are kind of meeting the image representation and the text representation inside this latent vector space. Okay. And then, of course, if you can express this type of scoring, how do you find the most relevant documents? Well, you compute this score for all the documents, and then you sort them by this score. So this is just what we do with BM25, right? And the scoring function is very similar, actually, to BM25, which is also a sum of something. But how do you go from Polygamma that's been trained on a lot of different tasks for question answering and whatnot to obtain representations that are good for retrieval, right? So I cannot really take the base model and then chop off this layer and chop off this layer and obtain some random vectors here and there and then say, oh, there's your retrieval model. That doesn't work. So the way they do this is that they add an adapter to the VLM. And the VLM is actually frozen. And frozen means that the weights here are not adjusted during training. They're frozen because this is a rather large model. It's like 2 billion parameters. Instead, they have this small adapter that they lay on top of the model. And we want to learn representations so that these tensor representations and the maxim scoring so that it ranks these relevant documents above those that are not relevant. And the way you do that is that you have this kind of triplet data. You have a text query, you have the image of a page that is deemed to be relevant, and you have an example of a page that is not relevant, right? So this is crucial for getting a good representation out of this, right? Without this step, it's going to produce worse results than random, okay? You have to have this kind of step. And here's the big block of relevancy training data. So this is the same thing with when the embedding model providers, they train models, right? They invest in this and how to train models, but they take some kind of pre-trained model and then they adapt it for retrieval. If it's a single vector text embedding model as well, similar thing, then they have a lot of tricks, like the guys here from Mixspread, to make this really work really well. But this step is crucial. And this is representational learning, learning representations that are useful for retrieval. So how does ColPali compare with other traditional methods? They released also with the paper a benchmark called the ViDoRe benchmark, which is because the issue is that with the current benchmarks, you're dealing with clean text, clean data, right? So they compare here with, here's actually an overview of what's in the data sets. Not a lot of documents actually, but still different tasks. And I've highlighted some areas here where archive-X questions or these ones, BM25 text extraction methods, you cannot extract text from these documents. So they are blank. You have to add OCR in order to get something. And here they also have, of course, the BM25 baseline. Pretty good baseline, actually. NGCD 565. And doing embedding retrieval, yeah, a little bit better. But ColPali is significantly better. And also, interestingly enough, even on the domains here, where BM25 works well, and embedding also works well. So these are text-heavy documents, not that many figures or infographics or whatnot, right? Even there, ColPali works really well. And the simplicity comparing to a system where you extract chunk, whatnot, OCR, and still ColPali that is just embedding the photo. I think this is quite amazing. Yeah, some samples from the benchmark to give you an idea of what's actually in the benchmark. So there's a wide range of document formats in the benchmark. Some are scanned. Here's a table from some nursery home. So it's actually quite complex, quite hard data set. And of course, we talked about ColPali. There's a lot of vectors here, right? There's one vector per patch in the image. There's one vector for the query. How can we scale this for practical applications? There are two components here in scaling ColPali for production. It's storage and compute, okay? And compute is more or less quadratic with the number of query tokens and the number of patch vectors, and of course with the dimensionality. And the storage scales with the number of documents times the number of patches times the vector dimensionality. And in this, I don't actually talk about like actual model inference, but you actually take the text input to the model to do the inference, right? That's a separate thing. So there are a couple of options you can do. You can reduce the patch vectors, and you can look at the vectors from a page, and you saw that in the screenshot of the page. There are a lot of white areas, right? They're not very meaningful. So if you take all the vectors, you can remove the redundant vectors, right? Those that measure the same information. And by doing this, you reduce the number of vectors P. So this reduces both the storage and the compute complexity. Then you can also reduce the position. So instead of using float, which uses 5 bytes per value, you can use 1 bit instead. And then you can replace float dot product with Hamming, for example. This is the same kind of learnings we've had from binary quantization. The guys from Mixspread trained their embedding models for quantization. Great way of reducing cost. So this reduces storage by 32x and compute by 4x. Plus, you can do a phase retrieval and ranking where you use HNSW or nearest neighbor search to first, you take those query token vectors, do a search for all of them, and then you re-rank using Maxim, and then you can use a different granularity. And top here on one of the benchmarks, float resolution gives you NDCD5 at 52, and you can pretty much retain the accuracy just by using binary representations. So I spent last 3 months on ColPali, so I've written 3 blog posts about it. So, but the too long didn't read is to reduce the precision and to use binary quantization, replace the dot product with Hamming, and then use HNSW indexing of these patch vectors. RAG, of course, it's important today. Lots of models that accepts rather large context window now, so you can actually input a lot of data to them. ColPali is the first stage, right, of such a system. When you are retrieving data for a RAG pipeline, you actually input the images that are retrieved from ColPali, and then you feed them into the generative model. And the amazing thing is that this benchmark, this long benchmark, which was just accepted, I think, to NeurIPS, shows that when you give the model screenshots of the pages, the accuracy is better for GPT-4 than when you're using OCR plus text. So even the generative models works really well with these type of source of information. So does it work for my data? Of course. So I'm more into the direction we're using VLMs because it solves so many problems. But there is a model checkpoint out there that the researcher trained, right? But that's just one model checkpoint in time, right? How can I adapt this to my data? You can fine tune it. Someone even made like a Hugging Face space where you can explore this, upload photos, and then have a generative model actually generate synthetic questions that would match this. So this would then form, you would do this, not in this UI, you will do this systematically. You will take your documents, you will have the model create questions, and this will create your relevancy data set to fine-tune ColPali so that your checkpoints is better than the kind of one that you can find on Hugging Face right now. Can't you use GPT-4 for this? I always get this question. You can, if you can fit all of your documents into the context window, and you can wait for 30 seconds. It works reasonably well. So ColPali is about doing an efficient retrieval. And on Friday, the authors also released a new checkpoint that is now based on a different, totally open source model. And this increases the NGTD by 5 points. So it's even better than the previous checkpoints. And I predict that we will see more checkpoints. We will see embedding providers as well going into this direction, because it's such an attractive direction where you don't have to do text extraction for retrieval. So I'm a huge believer in this direction. Yeah, and I have a lot of resources on this, and I don't understand why my timeline is not all about ColPali, because it's really a fantastic way of building search in this complex format. So, and more, we create a lot of notebooks and how to use it in Vespa and so forth. So, and I really recommend to play with VLMs for different tasks, entity extraction, whatnot. Try them out. So, yeah, then I can take your questions.
Thank you very much, Joe, for the inspiring talk. We have one question online that relates to retrieval of tabular data. So the question is, how does ColPali keep the context of tabular data? So if you have a table, a large table that has some headings, and you have these small 32 by 32 image patches, how is it able to keep that context even over a longer table?
Yeah, so this is more of a, let me see. So this is the kind of data that is part of the ViDoRe benchmark, right? So you essentially, all of these are just divided into grids, and based on the quality of the training data that you use to train the ColPali model, the checkpoint, right? That's how this works, right? So the model is not better than what it was trained on, but the initial pre-training step of the VLM gives it these kind of OCR capabilities, right? Reading text, and that's what we are exploiting here with this adapter. So, but I can't answer like specific, how the hell can it actually read this, and how the hell can it actually explain what I saw here with the performance benchmark, right? That's a little bit magic as well.
Okay, thanks. Questions?
Thanks for the great talk, Joe.
Thanks.
You mentioned one of the techniques to possibly reduce the number of vectors that you can do is, for example, look for sparse or white space kind of patches and remove those vectors. So I'm wondering, is this, the output of ColPali or Polygamma is is it high fidelity compared to this kind of, how many pixels are different colors? Can I do this thresholding after I compute the vectors, or do I have to do something else?
Yeah, that's a great question. So regardless of how the photo actually looks, the output embeddings are, you get 1030 vectors out. So the clustering approach you use is a post-inference stage. So it doesn't have to retrain the model in any way. You basically take the vectors and then you look at the vectors and say, I'm going to remove the ones that are very similar, right? Because they don't give you any value. And there are going to be a lot of vectors that are very similar because they're just encoding a blank space in this. And a team of researchers demonstrated that both for ColPali and ColBERT, you could reduce the number of vectors by 3x without having a very significant impact on the NGDG. So, yeah.
Okay, the online community has a question, or rather two questions about language-specific fine-tuning. One is if you're aware of a data set for fine-tuning, for example, for the Spanish language. And the other is, are you aware of any fine-tunes for any other languages like Norwegian, German, etc.?
Yep. So the ColPali paper actually evaluates, the model was trained purely on English data. They do evaluate it on a French test set that is part of this. So the initial snapshot has multilingual capabilities, right? So the text model that is part of Polygamma actually has multilingual capabilities. But in order to have it shine on your language, on your type of documents, this step is required, right? So no, I'm not familiar with any kind of checkpoints. Right? So I'm here more to talk about the direction. Like we're moving in a direction where you can use the VLM as the backbone instead of just using a text encoder. There will be checkpoints. There's going to be a lot more checkpoints, I think, in the coming months. So, yeah.
Have you seen any interesting approaches to handling contextualizing information being split across different pages?
Yeah, the first blog post that I did about ColPali, really, like, I really want to flex all the thing we have in Vespa, but I took it too far. And where I demonstrated that, hey, you can take one PDF, put it into Vespa. It's just a tensor with another dimension, which is the page. And then you can do a maxim calculation across all these pages and all sorts of things. And people are like, oh, what the hell is this? You know, it's too difficult. So I had to dumb it down, and one page is one Vespa document. But when you're retrieving, if you want to return, like, what's the most relevant document? Like, you're not in a RAG setting, but you have most relevant document. Then you can do like grouping aggregation on top of this, and then group by relevancy and like what's the best matching pages within the document. Yeah. So, but the first blog post I did is like, yeah, if you're into it, then you can read it. But I was so excited because it dropped. I had a few days of vacation actually, and this dropped, and I was like, what the hell? I have to demonstrate this with a notebook. And I was like, why are you working on the weekend like with this? Yeah, but this is so exciting. So yeah.
And I'm wondering how practical is to use ColPali in the real life. So how much time does it take to do inference of like a Gemma to produce 1,000 embeddings per page?
Yes, very good. So if we talk about, there are two things here. One is the cost of inference of the Polygamma model on the document side. On my laptop here, it's an M1. It takes 2.5 seconds on this M1. No, the MPS encoding. Encoding the query takes, I think, less than 100 milliseconds on M1. For Maxim, it depends on a couple of hyperparameters like HNSW, like you're retrieving with multiple query vectors, and then the ranking depth of Maxim. But the benefit of Vespa in this case is that you're not moving vectors around to the network. So you can move vectors into the CPU at the speed of memory bandwidth, right? Because if you see someone say, oh, we support Maxim in ColBERT, but the way they do this is that they first do a nearest neighbor search and then fetch all the vectors to perform the maxim, then watch your network footprint. It doesn't scale. Yeah.
Okay, I got another online question that's actually also would have been my question. Let's say I have a less complex PDF, which is mostly text, perfectly extractable.
Yeah.
Will ColPali still work and have a performance lead over something similar like ColBERT?
Yeah, this is a great question. We can go back to. So if I have text, so these subsets are text heavy, and BM25 works well. Regular embedding model with chunking also works well. ColPali is slightly better. I think if you change the baseline here with something like ColBERT, which is just text domain, it will bridge the difference. And if you go with Sean and talk to him about his mono T5 re-ranker, it's probably going to be maybe even better. Yeah, so if you're text heavy, you have your extraction routine, you don't have to start taking screenshots of things to embed them with ColPali. Yeah, so. And if you have your data already structured in your database, okay, you don't have to take a screenshot of it and embed it with ColPali. But I'm talking about complex documents here, HTML, MS Word, whatnot, right? That's the type of use case you want to explore this. But I do see that this will play a role in e-commerce search, because you can take the structured product title, the product description, and the image representation and have a joint representation of this. And then at query time, you have your text tokens. So you're attending to both the product text and the photo at the same time. Clip is also used for this, but it only encodes like either the text or the image. So you have to do some kind of model-T and add things on top of this to make it joint. ColPali just works. It will work.
More questions?
Hey, Joe, thanks for the talk. A question about explainability.
Yeah.
It strikes me that actually, if you've got the page and you're breaking the page up and you're using the maxim, presumably there is a way of reverse engineering that, so you can then say these bits of the page are the things that are most relevant for the query.
Yeah, that's a great question, Alan. So I'm not sure if it shows here, but they actually demonstrate this in the paper. The interpretability or explainability, it's easier to say, explainability of the model is that you can, since the maxim scoring really, you find the max patch for this query vector, so you can kind of highlight it in the image. So you can figure out from all of the text tokens, where they actually scoring in the document. So they have some nice infographics around this. We also did a demo of this in the text domain, the ColBERT with text, where you could actually highlight the text on the query. Why is it scoring like this? And that's a huge benefit over single vector models, right? Because you basically just take all the patches and then into one vector representation, but you have no idea why this document is ranking in this way. So, yeah.
Okay, one more question.
I don't want to be a fire starter, but how many search engines in this room can do this kind of multi-vector late interaction thing? To build on your question on Twitter, why is your Twitter empty of talking about ColPali?
Yeah, it's a question. I know engines that can do multi-vector representations. There are quite a few. There are pros and cons, but I know that Quadrant has support for multi-vector representations. I think LansDB has support for multi-vector representations, and of course Vespa with our tensor framework. I think the Lucene-based engines don't have support for it because they rely on Lucene. I know that there are some tickets and issues around it, so it might happen. And also, I think you can probably hack around it also with PG vector in some cases, but not with combined with HNSW indexing. So I think that's a fairly accurate summary.
Thank you. We are at time, so we have more questions online. My suggestion would be to just maybe contact Joe.
Yes, you
maybe
find me on
even
Twitter.
Twitter, yeah.
Just shout at me there. I'm there. So, all right.
So yeah, fill up his timeline, and thank you, Joe.